is, and I'll just make this. I think I've said this before, but it's worthwhile making the point again. That I know in common language, when we talk about codes, people often mean things like ciphers, encryption. But in computer science, there's a difference between cryptography and codes. So remember, it's a bit like, crypt in the church, something that's usually below the ground, but something that's hidden away in secret. So here we want to hide information, or make it secret. And here, we actually want to do quite the opposite. We want to keep the information as unhidden as possible, but what's the best way of saying this? So as unhidden as possible, we want to make it as transparent as possible. So this is all about how do we, so with cryptography, we want to transmit information in secret. In coding theory, so this is part of, there's a whole branch called coding theory. In coding theory, what we want to do is transmit information as transparently as possible so that the person at the other end has no chance of making any mistake, or as little chance as possible of making a mistake about what's been received. So, so the idea would be transmit as openly accurately as possible. And one way of doing this is you want to be able to send things, transmit information, so that if an error has been made in the transmission process, then it can be detected and possibly corrected at the other end. So the idea is something like this. I mean, remember that we're only sending zeros and ones. So suppose we want to send the message 0, 1.
Excuse me, Chris.
Yep.
Are you sharing your screen? I can't see anything.
Oh, sorry.
Your computer camera.
Right. Sorry about that. I thought I was sharing a screen.
You might be. Maybe it's just my one
screen.
No,
I forgot to share it. Okay, so can everybody see a screen now? Okay, so the point about cryptography is that crypt meaning secret, we want to hide information that we transmit. In codes, this is part of coding theory, we want to transmit as accurately as possible and in a sense as openly as possible. So we're not trying to hide the information. So in computing, we tend to send zeros and ones. So suppose we've got a message that looks like 0, 1, 1, 0, 1. We want to transmit that. So you can imagine that, I mean, this happens in real life. You've got a little 1 watt or 4 watt transmitter on a satellite that's out in deep space. And I mean, 4 watts, if you imagine a candle on the moon and you've got a telescope trying to see the candle. It's kind of that situation. So you've got this little transmitter and it's trying to send 0, 1, 1, 0, 1. But it knows, well, you know that because it's such a weak signal from the radio transmitter on this satellite that's out near Pluto or further out, that errors are going to happen on the way, so that these signals just get corrupted. So you might end up receiving 0, 1, 0, 1 0, so that this one gets corrupted. So that's what's sent, that's what received. But unless you put a plan in place, you have no guarantee that what was received was what actually was sent. So what you try and do is build in some mechanisms so that you can detect if an error has occurred, that a bit has been scrambled, or even if you can, or possibly to correct that error. So, I mean, one possibility would be, instead of sending just the 4 or 5 bits like that, you might decide to rely on a bit of redundancy, and you might send 0 0 0 1 1 1 1 1 1 0 0 0 1 1 1, so that instead of sending a single 0, you send 3. Instead of sending a single 1, you send 3. So that way, if any corruption occurs, you've got some chance of knowing what might have gone wrong. So you send this, and then what's received at the other end is 0 0 0 0 1 1 1 1 1 0 1 0 1 1 1. So that's sent. This is received, and you can see that a couple of bits have been corrupted. Now, the point about the redundancy is that if I receive that, then I'm going to guess that only 1 bit was changed here, not 2 bits. So I'm going to guess that this should have been 1 1 1 rather than 0 0 0, because it's more likely that 1 bit was corrupted than 2 bits. Same thing here. If I receive this, then I'm going to guess that it should have read 0 0 0 rather than 1 1 1. Again, because I'm assuming that it's more likely only 1 bit is corrupted. Now, it can't be guaranteed that, but so the idea is that I can add in redundant information to make sure that I've got a better chance of recovering what was intended at the beginning. Another way of doing this is to add a bit of extra information, tack a bit of extra information on the end, so that I can check the information at the end and see if this is actually a genuine message. And that's what happens with barcodes at supermarkets. Credit card numbers. Do I have something here? Yes, I'll find something on my desk that has a barcode on it. Surprisingly, the number of things that don't have barcodes on them. So this will do. Yeah. Okay, I have a bottle of ink, and let's see. Yep. So here's my barcode, and each of those bars, these sequence of bars encode this number, and the barcode reader reads it, and you've all been caught up where the barcode reader doesn't read the right thing, and somebody's got to come and manually check it in or type in the number. Same thing with credit card numbers. If you're making purchases or copying a computer file, there are mechanisms in place to check that or check for errors. Copying a computer file, one of the things that I think if you look at copying the manuscripts of the Old Testament, which was written in Hebrew, so what people would do in the old days was, because they were copying things out by hand, I mean, we're talking about hundreds, thousands of years ago, they were copying things out by hand, and what they would do is just count up the number of occurrences of each letter in the manuscript. So if your original manuscript had, 101 alepphs, and your copied manuscript had 102 alepphs, then you know a mistake had occurred somewhere. Credit card numbers have these security systems in place as well. So what we're doing is trying to put in place a simple means of checking the data to see if it's plausible that the messages or the data or the thing that's being transmitted is a plausible or a legitimate barcode or a legitimate credit card number. If you were in front of me, I'd ask people to put up your hands. Who's put in your credit card number or an ID number into a system, and then it spits it back and says, no, that's not correct. You must have made a mistake. Yeah, a few people. And how does it know that? Well, there's a mechanism built into the construction of the number. Our credit card number has four lots of 4 digits. They're not just random digits. They're constructed in a particular way, well, up to a point. Pretty common errors are that you transpose two things. So instead of writing 1, 2, 3, you write 1, 3, 2, or more to the point, instead of writing 1, 3, 2, you might write 1, 2, 3, because that's you get into the groove of 1, 2, 3. You can things like checking if files are corrupted, digits being in a credit card or any other thing being swapped around. So what we want to do is try and detect errors and correct errors. I don't know if any of you still play CDs, but CDs have built to them codes that detect errors in them, digital TV signals. So you've got a scratched CD, some electrical interference with your TV signal. Your CD is actually quite sophisticated. If it picks up a mistake, certain sorts of mistakes, it actually can fix it on the fly and knows what to do. Kind of a bit like this. It's a bit more sophisticated, but if you received 011, it should have been 111, and you recreate that bit as being a 1, so 01101. Error correcting codes like that is actually a lot more sophisticated in general, so we won't do that. We're just going to look at how to detect errors. Okay, so I just showed you, here's my bottle of ink. So I've just shown you a bottle of ink with this barcode. Here's a barcode from a packet of Just Right breakfast cereal. EAN, 13-digit barcode, so 1, 2, 3, all the way up to 13 digits. There's information encoded, notice I said encoded in this. So the first 12, so up to there, the first 12 digits tell us about the country, the manufacturer, and something about the product. The 13th one, though, isn't just random. It isn't made up. It depends on the first 12. And there's actually a formula to tell you what that 13th one is. And that formula is designed in such a way that it will detect certain errors in some situations. So it's called a check digit because suppose I swap 0 and 5 around, then that 6 wouldn't be the right check digit. And so the scanner would say, oh, you've made a mistake. You've typed in the wrong number. Then you go back and you say, oh, yes, I transposed 2 numbers. Or you misread the 1 as a 7. And again, if you change the 1 into a 7, that 6 would change. So what we're going to do is look at the formula for that 13th digit in these EAN 13 barcodes. So the check digit is always between from 0 to 9, and so congruent to 0 mod 10. This is using this modular clock face arithmetic. So the idea is you number the positions from left to right. I think it's from left to right. Yep, number the positions left to right. So let's zoom in. So the first position is 9, the second position is 3, the third position is 1, the fourth position is 0, the fifth position is 0, etc., etc., etc. So we talk about the odd and even positions. So how do we calculate 6 from there? So how do we calculate, where am I? How do we calculate that 6? Well, what we take is we take all the odd numbered positions. So not the odd numbers, but the odd numbered positions. So if we look at the odd, if I take, zoom out again. So if I look at the positions, the odd numbered and the even numbered, 9 is in the first position, so it's in an odd numbered position. 3 is in the second position, so it's in an even numbered position. So if I write it this way, it'll be a bit clearer. So 9, 3, 1, 0, 0, 5, 0, 5, 5, 5, 5, 5, 3, 7, 3, 7, 2, 8, 2, 8. Don't worry about the 6 because that's going to be the check digit. So the 9, every second one is in the first, third, fifth, 7th, 9th, 11th position, second, 4th, 6th, 8th, 10th, 12th position. So odd positions, even positions. And so what we do then is we basically take these ones in the odd position and add them up. And then we take those ones in the even positions and add them up. Triple that sum in the even positions and add it to that sum. So if we do that, what's the sum of the odd position numbers? So 9 plus 1 plus 0 plus 5 plus 3 plus 2. They're in the odd position, plus 3 times, so I goofed a bit here. I said put the checksum aside. I should have. So the check digit 6 is in the 13th position, so that gets calculated in the formula. A mistake. So 9 plus 1 plus 0 plus 5 plus 3 plus 2 plus, I'll put a little line under there. That's our check digit, plus 3 times the sum of the even positions, 3 plus 0 plus 5 plus 5 plus 7 plus 8. And if you do the arithmetic correctly, this is 9. Let's see if I can do this correctly. 10, I think this comes out to be 26. I think if you add this up, that comes 28. Okay, 3 times 28 is 84. Okay. We're adding 26, so that's equal. It's equal. At 26 plus 84 is 110. It's a final digit of 0, which means that it's congruent to 0 mod 10. So this is congruent to 0 in the mod 10 arithmetic. So mod 10 arithmetic is really easy. Mod 10 arithmetic, 17 is congruent to 7 in the mod 10 arithmetic. You're just looking at the final number. 2,316 is congruent to what in the mod 10 system? Just the 6 on the end. Because if I divide that by 10, what do I get? 231 with remainder 6. Okay, so that's actually what's happened on that slide. Some of the odd, this means odd. Let's put odd position digits. Odd position. Odd means numbered. I think of the odd positions, the even positions. So the checksum is 110 divisible by 10, which means that at least it's a valid number. It's a valid code. Now you can see what's going to happen. The manufacturer comes along and says, country of manufacturer, a number for the manufacturer itself, a number for the item. What checksum digit should be put in? Well, basically, the manufacturer says, I know what those numbers are, but I don't know what the checksum is, so I've got to figure out what that is to make this sum congruent to a multiple of 10. So that's where we're going. And that's what's happened here. So we've got some Vegemite. It's missing its check digit. So the check digit that would normally appear there is missing. We're going to pretend that that's called D. Okay. And we're going to try and figure out what D is. What is that missing checksum? So we go through and we say, what are the even numbered position? What are the odd positioned things? So 9, 0, 6, 0, 5, 5, and then the missing one, D. So these are all the digits in the odd positions. The digits in the even positions are 3, 0, 5, 6, 8, 1. So 3, 0, 5, 6, 8, 1. Add them up, multiply by 3. Add these up. Okay, so we've got 9 plus 6 plus 5 plus 5 is actually 25. We're still adding D. So the idea is that we want to find D. 25 plus D plus 3 times 23 is 25 plus D plus 69. That's D plus 94. Now, you ask yourself, what do I have to add to 94? What do I have to add to 94 to get a multiple of 10? Well, that's easy. Okay. I simply have to add 6. Because if I add 6, I get to 100, and 100 is a multiple of 10. So D is the number I have to add to 94 to get a multiple of 10. So that's congruent to 0. So what I'm doing is, when I say find D, I'm saying D plus 94 is congruent to 0 mod 10, or D plus 94 is a multiple of 10. Now, what's the closest multiple of 10? Next one up is 100, and that means D has to be 6. So the check digit is 6. Okay. So, so there it is. That's what it should be, 6 just there. Now, what if a mistake? So we know that the Vegemite barcode actually should end in a 6. So what would happen if the scanner or somebody writing this down wrote down 93006, and then instead of writing down 5, wrote down the 6 again? So suppose it scanned 9300666 66 instead of 9300065, and then continued on. So what would happen? Oh, sorry, it was scanned as a 2, my mistake, reading ahead. So it was scanned as 930062065. So I suppose the scanner did that, or you wrote that down. What would happen? Okay, so you take 9 plus 0 plus 6 plus 0 plus 5 plus 5 plus 6. Okay. Add 3 lots of the even numbers of position, so 3, 0, add 3, 0, 2, 6, 8, 1. Multiply by 3. Add the odd numbered things together, so we get 3 lots of, that's 20, that's 31. 3 lots of 20 plus 31 is 91, and that's not congruent. Okay, so not a multiple of 10. That's worthy of an exclamation mark. So the fact that it's not a multiple of 10 says that there is an error somewhere. So that error has been detected. So it doesn't tell you what the error is, right? You'd have to do a bit more investigation, but it would say that that's not a valid EAN number because you've put something wrong somewhere. It can't tell you that the 6th position has been changed. All it can tell you is that there is an error there. So part of what's happening is, something that's can happen more generally, which is that this checksum formula can detect a single digit error. So if I make a mistake in just one digit along here, then the checksum formula will say, no, that isn't right. So I could change 6 into any other number, 7, 8, 9, 0, 1, 2, 3, 4, or 5, and run it through the checksum formula, and I would get a mistake. But if I change 2, I might not. So the thing here is that we can detect any single digit error. So if only exactly one of the 13 digits is incorrect, then that checksum formula will fail. We call, now up here, strictly speaking, what we've done here is that this is 1 times that, and that's 3 times this sum. So you take sum of the odd position numbers and multiply it by 1, sum of the even numbers positions multiplied by 3. This 1 and this 3 are called weights. So the weights of 1 and 3 are both relatively prime to the modulus of 10. So basically 1 and 10 don't have any factors in common apart from 1. 3 and 10 don't have any factors in common except for 1. So they're relatively prime, co-prime to 10. So that's one reason it works. I mean, there's actually quite a bit of mathematics involved in that to actually explain why. Turns out, though, that while this is what is actually used, there's a reason for it. There's a bit of a roundabout way of getting there. But if you take just a simpler formula, just add up all those digits. 9 plus 3 plus 0 plus 0 all the way up. And use that as the basis of making the multiple of 10. Then that simpler formula would also detect a single digit error. So why would we bother using a more complicated thing? Well, it turns out that this more complicated formula will detect another sort of error, transposition. So suppose instead of writing 650, we got 605, or instead of 16 at the end, you wrote 61. That sort of transposition also gets picked up with that more complicated formula, which the simple sum of all the 13 digits wouldn't pick up. So a simple sum of all 13 digits picks up a change in one digit, but it doesn't pick up any transposition errors. The more complicated thing, where we're weighting the odd numbered digits with 1 and the even numbered digits with 3, picks up two sorts of errors: a mistake in a single position and a transposition. So that's why it's a better thing. It just does more for you. So here's an example. The 9th and 10th digits, here's our just right barcode. Yeah. And suppose we take the 37 here. Suppose the 37 was transposed into 73. So instead of reading 37, you read 73. So let's check this to see if it's a valid EAN. So this is a transposition. Okay. Odd numbers positions, 9, 1, 0, etc., add them up. Even numbered ones, 3, 0, 5, add them up. Multiply by 3. Multiply those by 1. You end up with 30 plus 72 is 102, which is not a multiple of 10. So swapping around the 3 and the 7 to 73 gets picked up. So that is another error, is an error that gets picked up by this more complicated formula. Yeah, but there's more. This is a really fascinating area because what might happen might not be always the thing that you think happens. So this transposition error got corrected. So you might think, oh well, I sort of started to mislead you before. You might think, well, maybe all transposition errors get corrected. And it turns out that that's not the case. So if we take the 10th and the 11th, so we've got 7 and 2. If you swap the 7 and 2 to 2, 7, so transposition error there, and apply the checksum formula to this, you end up with something which is a multiple of 10. And you think, oh, no mistake. So what's happened is that this transposition has not been detected because it comes out as being a valid checksum digit. So this more complicated formula, life is not as easy as saying, well, it picks up every transposition. It picks up some, but not all of them. But kind of most of them, it's just 7 and 2 happen to be, if you like, just right in relationship to each other and to be next to each other, that this doesn't get picked up. And in fact, a little bit of work, I mean, this is where the mathematicians come in. You can actually detect all transposition errors except for one sort, where the two numbers next to each other differ by 5. So we had something, something, 7, 2, something, something, and that was transposed to something, something, 2, 7, something, something. This didn't get picked up because 7 and 2 differ by 5. Sorry. 7 and 2 differ by 5, so swapping them actually doesn't affect the checksum algorithm. So the summary for this is that these EAN3 barcodes, 13 barcodes, will detect a mistake in any single digit and almost every transposition except for the ones where the two adjacent positions differ by 5. So if you look here, if I swapped this 5 and 0 around, so that 5 and that 0, if I swapped around to be 0, 5 and ran it through the checksum algorithm, then it would come out as being valid. It wouldn't get picked up because they differ by 5. But if I swapped 6 and 5 there, that would get picked up because they differ by 1. Okay, credit card numbers. It's very, very similar, except that instead of having a weight of 1 and 3, credit card numbers have different weights. So I said, where are we? Okay, 4 lots of 4. The first 15 are the actual number. The last one, the 16th, is the checksum. So it tells you which bank, which company, and the account, and then that's just a checksum. So the check digits calculated in the same way. We take the odd positioned, so 4, 0, 4, 0, 0, 1, 3, etc., add them up. But instead of multiplying them by 1, like the EAN, we multiply them by 2. Then we take the even position digits, go 0, 0, 0, 2, 4, 6, 8, 9. Okay. We add them up, and instead of multiplying them by 3, like the EAN, we multiply them by 1. So there's really a 1 times in there. So weight of 2 and 1 instead of 1 and 3. Okay. However, this does have a few problems. It's not necessarily the best way of doing things, but it's convenient. This checksum formula doesn't even detect single digit errors. So Okay, what I'm going to do is I'll actually continue and talk about this at the next lecture. I went a bit astray earlier. So we'll just finish here with a reminder, with a statement that this particular checksum formula doesn't detect all the errors, or single-digit errors, and we'll just work through an example why and a way of a way of improving that. Okay, let's finish up there, partly because I've got another class to go to at 4 o'clock, and we'll finish up this at our next meeting, which I think is Thursday. Is that right? Yep. Okay, so we'll finish up there, and yep, cheers. We'll see you on Thursday.
Thank you.
Yeah, ciao.